My name is Yuri Gordienko. My topic is dedicated to our presentation on the title Context-Aware Data Augmentation for Efficient Object Detection by UAV Surveillance. The work is performed by a group of authors from National Technical University of Ukraine, named after Igor Sikorsky. Content of my presentation is standard, and I am going to introduction. We are evident of, for example, the current evolution of deep neural networks, which demonstrates a very high performance and high applicability for different tasks, for example, for object detection from drone imagery, namely image and videos obtained from cameras installed on drones and unmanned aerial vehicles. Recently, it becomes a very intensive field of research and used to detect some very tiny objects like pedestrians, pests, bikers, skaters, vehicles, and more bigger sizes objects like car, buses, and so on, for various applications, from urban logistics to general logistics, traffic management, manufacturing, and other all applications. What is main motivation of our paper is evaluating some techniques to improve the current state-of-the-art deep neural networks, which used for object detection in this context, in the context of drone imagery, and in the presence of the following errors. For example, in labeling procedures, first of all, then availability of different classes of quite similar by shape, but small by size, for example, and different by dynamics. The main incentive is to use the current DNNs and current available datasets to improve in the view of the real-world data. Why we are interested in real-world data? Because if you go the background and related work on this way, you can see that the whole workflow to obtain drone imagery is like this. You have some drones, they make some snapshotting and obtain some result, image like this or videos like this with some bounding boxes around object of interest. Object of interest can be like this, for example, or like this in man, or for example, not only in the shape of bounding box, but in the shape of pixel-to-pixel object segmented region of interest. That is why the very big volume of data was collected, but the following problems also were observed. First of all, some availability of shadows, for example, road marks, or for example, some difference in colors, or occlusions created by objects which are not of interest, for example, for our task. That is why all these things actually lead to decrease of performance of the models. But in addition to this, we need to understand that some objects can have very small size. In contrast to big size objects, for example, like cars and buses, pedestrians are quite small, and aggravated by human or algorithm-related errors in labeling procedures. That is why we attract your attention to how these problems can affect on very good current DNN models. For example, we used YOLO version 4 models, which is very good known for current moment, demonstrate very high performance and described in details elsewhere. Our idea was to attract attention to model real-world data, which can come from variety of sources, be very complex, unusual, it have an unstandard structure, but mostly important in our context, can be incorrectly annotated or not annotated at all. This is so-called relatively dirty data sets, which are used very widely now in practice situations. That is why there is a need for new, highly efficient approach for application of these state-of-the-art DNN networks for work with real-life dirty data sets. In this context, we attract your attention to methodology. First of all, what kind of data sets we use, and how these data sets, which can be clean or dirty, and contain proposed here context-aware data augmentation, can be used with these very well-known models under different branches of workflow. First of all, dataset. Dataset is created on the basis of Stanford drone video imagery dataset, which was available on the site of its developers, but now it's not available, but it's available elsewhere. We created derived version of this dataset with some image. Some examples of this image are presented here. For example, you can see the man object, biker object, skater, car, cart, and bus, with some drawbacks which are evident here. For example, this bounding box covering not all person, this bounding box also not covering all square of bus, and so on. This is additional, not necessary background. This car not bounded at all. It's all create impression how bad can be the dataset. But mostly important that some man-made errors created by operators, for example, red ellipses, mentions the situation when cars were missed at all, or for example, so-called algorithm-driven errors by erroneous extra interpolation of object movements can be provided also. For example, you can see they denoted by blue ellipses. For example, this car is going by this way, and on this image it's properly surrounded the bounding box, but on this image it's disappeared, but bounding box exists. It's an error. That is why to improve our understanding of such an influence of such a problems on performance of SOTA DNNs, we apply extended data augmentation procedure. I need to know that we use standard data augmentation procedures, which was good for such applications, and also we used another data augmentation procedures which were not so good at all, and because they were counterproductive. We mentioned them minus and plus as a whole. But we propose quite different procedure which is based on the increase or decrease bounding box. If we assume, for example, the ground truth bounding box was in red color, we propose automatic decrease or decrease by this value of percentages, and with these notations, for example, in, out by number of percentage, and apply them to original dataset and create derived datasets, which were used additionally to original dataset. It's so-called context-aware data augmentation from our point of view. Let's consider how it influences our results. But first of all, we need to describe the models and workflow on the basis of this additional context-aware data augmentation. First of all, we used a YOLO version 4 in this basic version, which is described in details in this walk. And you can see that all reference numbers here go into the numbering in the main text. We performed usual training with measuring the following metrics, and all these metrics were determined after 1000 training epochs, and highest values of validation of this value were saved for each experiment that will be described later in the tables and in the diagrams. First of all, the following list of experiments should be denoted. For example, original experiment was based on so-called random weight initial weights of model YOLO V4 for original dataset SDD with output of model with subscript 0 or O. Then the additional experiment in5 included, except for original dataset, included additional dataset created on the basis of context-aware data augmentation with change of by 5% of the bounding box for all objects. After training in the same way, we obtain model with subscript 1. Then additional data augmentation in the opposite directions of change of width and height of the bounding box was applied, and actually this dataset contains from 3 subsets, and we obtain model 2. That is why step by step we obtain different modification of these training models, and all of them were evaluated on non-scene evaluation datasets. The whole diagram of all these procedures is described here and in details described in the paper. Finally, what kind of result it allows us to obtain? First of all, it allows us obtain the following procedure for estimation of our statistical reliability of the results. We applied so-called five-fold cross evaluation, which is in contrast to k-fold cross validations, means that all evaluation set not foreseen for training models was divided in 5 folds, and for each fold we measured all metrics and then estimate mean and standard deviation of all metrics. That is why by this cross evaluation we can estimate the statistical reliability of fluctuations of our measures with relation to different data in evaluation set. Then all models were evaluated in a full evaluation subset. It allows us to perform the reliable estimation how big our difference. As to the original training experiment, it was like standard. We estimated evolution of the mean average precision and loss and determined all necessary values for dirty and clean version of dataset. Finally, it allows us to obtain the following, for example, for cross evaluation, the following values for each fold. This estimation of mean, as I said before, and standard deviation values for all metrics which we described in this context for row classes. And you can see that standard deviation was not more than 1%. It's related to the dirty dataset and for some so-called clean subset of dataset which was manually checked and excluded all errors that were performed by operator or algorithm. It allows us obtain estimation that again the error as a whole is not higher than 1% for dirty and for clean dataset. That is why after this we measured the same things, mean and standard deviation values, for each class. And we obtained quite different values because for some classes the error was much smaller, and for other classes it was. If we compare the same metrics but after context-aware data augmentation, if for example we compare original one results and all other after each procedure in the workflow of context-aware data augmentation, this is especially interesting to observe not only for all classes but per classes, because for all classes we averaging in quite different behavior for different classes. If we consider the same situation for different classes, then we can have here much more pronounced persistence of improvement of our model. For example, for in 5 out 5 experiments, we can see the best values for dirty and for clean subset. And this difference, this improvement of our performance is approximately from 2 to 3%. And if you compare with standard deviation error, it was approximately 1%. That is why this context-aware data augmentation, at least by 2-3%, allow us to improve the performance of our models even on clean and dirty data sets. That is why if we provide, for example, the same approach for cart and bus, it's not so good. For cart, it's in the measure of error, standard deviations. For bus, it's much better, much worse, pardon. Why? Because if we compare all these situations, I mean, if you consider the structure of bus and the structure of man, the roof of the bus have very homogeneous texture, and this texture is very similar to homogeneous texture of, for example, road or grass or other backgrounds. That is why some mistake can appear in this context. What is more important here also that is non-commutative nature of context-aware based retraining procedure. Why? Because when we make procedure of in 5%, it means we decrease size of bounding box by 5%. Actually, we increase signal of noise ratio, and by this way we increase signal of noise ratio for whole data set in the part of added subset. But if we add out 5 subset, we increase variability of data in this set because we include much more information of background. It will lead to decrease of signal to noise ratio in some extent, but in 5 out 5 procedures. And it can be different for various applications and data sets. And we see that it should be said for some classes, this can be, problem object detection was considered for Stanford drone dataset. For dataset part which was put as open access SSD frames, context-aware data augmentation was proposed. It allows significant improvement of performance in comparison to experiment without CADA, and allow to get MAP values on dirty real dataset similar or higher even than on clean datasets. This effect can be explained by increase of signal to noise ratio for object to background pairs after context-aware data augmentation. It should be noted that non-commutative nature of CADA-based retraining procedure can be observed. And the best strategy consists in first in, then out CADA procedures. In general, it allows us to support the trainer shifting from model-centric to data-centric approach to artificial intelligence problems. It was mentioned, like it was mentioned in Andrew Ng opinion. For this, I am finishing my presentations. In the first my word, I like to say thank you for your help to Ukraine, because you know on 24 February, Russian Federation started the invasion on Ukraine. But no, it's not invasion, it's war. This war against not only Ukrainian independence, also against current democratic values, principles of humanity with genocidal intent. From second day of the war, I served as volunteer soldier in Battalion of Kiev Territorial Defense, right 2 kilometers near from Bucha massacre place. Then I returned to my university. But when you're watching this video, Ukrainian people are dying from terror Russian attacks. For example, right now, preparing these presentations, I stopped several times because I hear again from the streets, attention, air raid sirens in Kiev, please proceed to shelters. This war will be very long, up to dismantle of Putin's regime in Russian totalitarian empire. But we will win and defend our independence and democratic values. Every day Ukrainians are grateful to all civilized people, to you, who every day provide their support to Ukraine. Thank you. We feel this, we thank you and them for this. Thank you very much for your attention.